Hi, this is the blog in which I talk a little bit about the work that I am doing, have been doing here at the observatory. I'm on top of the mountain at the moment. It's just after 7 a.m. and I've just finished a night shift using the 1 meter McClellan telescope, which you can see behind me. The observatory is located in the Mackenzie Basin in the Canterbury region of New Zealand, so we're pretty much right in the centre of the South Island here, in the Southern Alps. And this whole region is a dark sky reserve, which makes it pretty much perfect for observing the stars. So this is the telescope itself, the 1 meter McClellan telescope. It's called the 1 meter telescope because the main mirror at the bottom is 1 meter diameter. It was the largest optical telescope in New Zealand until about 10 years ago, when it was usurped by a 1.8 meter telescope, which is located about 200 yards up the road from here, which I will show you in another video. So the primary mirror can be removed, and it is removed every year, I'm told, to get recoated. And there is also the choice of two secondary mirrors. So you can see the black thing at the top there, that's one of the secondary mirrors. And you can swap that around in order to change the focal length of the telescope. So at the moment, the secondary mirror is the smaller of the two, and this is the one that I am using to observe stars. This is good for focusing on sharp, small objects. For a shorter focal length, they swap it out for a larger mirror, and then they can observe slightly larger areas of sky. The telescope sits on a fairly hefty equatorial mount, which allows it to track the stars across the sky. And the dome itself will track the motion of the telescope as well. So when it comes to moving the telescope from one position in the sky to another, you can use the old-fashioned method of steering the telescope using a keypad. So you can go north, east, south and west and all that kind of stuff and steer fairly accurately to the stars. For finer tuning, there is a nice user interface as well, where you can control the right ascension and declination from the nice warm control room, which I'll show you in a minute. The old-fashioned way using the keypad is better because it limits the possibility of the telescope driving itself into the ground, which nobody wants to happen. In the event that it starts to rain, there are sensors dotted around the dome which detect moisture, and then if the levels get too high, there is an alarm in the control room which starts blaring. So in that situation we have to run in here and close the dome fairly quick. So far I haven't had to do that, although it is quite sensitive, so even if there is some very slight cloud in the sky, sometimes it starts going off. So for the first few times when I was observing, I got a bit of a fright and came running in expecting a deluge of water when the sky was pretty much clear, but there was a small cloud. For the observations that I'm doing, looking at variable stars, the smaller secondary mirror focuses the light into a spectrograph known as the High Efficiency and Resolution Canterbury University Large Echelle Spectrograph, which is known by the slightly catchier name Hercules for short. So the light enters the telescope and comes down into this here, which collects the light and feeds it into a optical fibre, which then channels the light into the spectrograph. And Hercules itself lives in a temperature controlled room where the conditions are kept optimum for its operation, so there's no reason for me or anyone else to ever really go in there. Instead, I operate the telescope and the camera and things like that from a control room around the corner. And this is the control room. So I sit here for most of the night, for about 12 hours, controlling the telescope. So like any other camera, you can vary the exposure time depending on how bright the object is that you're looking at. So for dimmer stars, you'll have a longer exposure time, and for slightly brighter stars, I'll have a longer exposure time. For the stars I'm looking at, it varies from 300 seconds for very bright stars to about 1500 seconds for the dimmer stars. So the brighter stars are about maybe magnitude 5 or 6, and then the dimmest stars are magnitude 7, getting up towards 8. So the average is about 1200 seconds, so that's 20 minutes. So each photo takes about 20 minutes. And what you can see on the screen here is one of the spectra for the thorium lamp, which is what we calibrate the spectra of the stars against. So every time I take an exposure of one of the stars, I then take an exposure of a thorium lamp. And the spectrograph allows us to cover a very large range as well, from just under 400 nanometers up to about 850, 900 nanometers, which allows us to fit an entire spectrum of a star onto one exposure. By taking a large number of these spectra over several weeks, it allows us to see Doppler shifts in the light from the star, which come from very slight vibrations in the surface. So the ultimate aim for this data would be to use it in a very similar way to how seismologists here on Earth use vibrations from earthquakes to get a better picture of the internal structure of the Earth. So we should be able to use the vibrations on the surface of these stars to really give us a much better understanding of what makes the insides of these stars tick and how they are structured, and also give us a better understanding of the evolution of these stars as well. So that's a very quick summary in a nutshell of what it is that I'm using the telescope for. I'll keep doing updates over the next few months when I'm back in York about what it is that I'm doing with the data and some of the stuff that we're finding. So if anyone is interested, then I'm sure you will find me very willing to talk about it. So aside from the work that I'm doing using the telescope to look at stars many, many light years away, there are also other projects that use the scope for things that are slightly closer to home. The primary one uses the scope for about 2 weeks out of every month to look at near-Earth objects. So these are asteroids anywhere in size from maybe a few meters up to a kilometer, and these asteroids are known to come quite close to the Earth, hence the name near-Earth objects. And the job of the people who observe those is to make sure they're behaving in the way that they're expected to do and not posing any danger to us. So they're just tracking these, and they use the different configuration of the telescope with the larger mirror giving a larger field of view. And what they do is focus on an area of sky where they expect to see the near-Earth object coming through, and then they will take a series of photographs, and as the object, the asteroid, passes through the frame, they will see a series of staggered images, or hopefully see a series of staggered images of the asteroid coming through. Now, aside from that, a couple of weeks ago the telescope was used for a very interesting little project. A French astronomer came down to observe a occultation of a asteroid in between Saturn and Uranus named Chariclo. Now the occultation would usually just be one light dip, so the asteroid will pass in front of the star and then the light will dim slightly and then the asteroid will disappear from in front of the star and the light will go back up again. Now with Chariclo, the asteroid, they expected to see 3 light dips. So there would be the main light dip, which would get rid of most of the light from the star, and on either side of that main light dip they would expect to see a very slightly smaller light dip. And what this means is that when the asteroid is passing in front of the star, there is something on either side of it also dimming the light. And the thing that is dimming the light on either side of it is a ring. And Chariclo was one of the first asteroids ever discovered to have a ring. Now what got me about this observation was that the astronomer came down all the way from France, and he was doing a couple of these observations. The Chariclo was expected to occult a number of stars over the course of a weekend. But these occultations only last for a fraction of a second, so he had to fit a very
high-speed camera to the back of the telescope in a similar way to the work done by the people looking at near-Earth objects. He takes a number of frames. But he had to take about 100 frames in a second period, and he didn't know whether or not the weather would be any good, so he just came down here to use the telescope on a wing and a prayer, hoping that the weather would be suitable for the observation. Now, as it happened, it was, and he got the data that he needed, but it makes me think, I'm sat here for weeks at a time and I can afford to take exposures over 20 minutes, and if it's cloudy I can go back and do another one, whereas his data relied on a fraction of a second in one day and one star being in the right place, and it all worked out, and I love that kind of precision. I thought it was very exciting.